This sixth quarterly film report to the National Aeronautics and Space Administration covers progress during October, November, and December 1960 on Project Saturn, under developmental supervision of NASA's George C. Marshall Space Flight Center at Huntsville, Alabama. Shown here in a 1/10 scale model, the Saturn vehicle is designed for use in orbiting payloads in excess of 10 tons, launching Mars and Venus probes, effecting soft landings on the Moon, and injecting manned satellites and space stations into orbit. A major milestone in the Saturn program was approached during this report period with virtual completion of assembly of the first Saturn booster, depicted in this quarter-scale model. The booster, or S1 stage, for the first flight vehicle called SA-1 was scheduled to be released to the Marshall Center Quality Division on January 9, 1961 for inspection and checkout. Basic steps in the booster assembly, which began May 28, 1960, may be traced in this series of drawings, including positioning of the tail section on the assembly fixture, connecting the 105-inch diameter center liquid oxygen tank to the tail section, attaching the spider beam assembly, and installing the 8 70-inch diameter LOX and fuel tanks. Here, the complete booster is shown on its fixture, ready to leave the shop. Final assembly accomplished this quarter included installation of the booster's 8 H-1 engines furnished by Rocketdyne, the upper stage support used for attaching the Saturn's upper stages, upper stage support shroud, and the 4 instrumentation canisters which carry control and telemetry equipment. A new series of static test firings of the modified Saturn test booster, SAT-1, began this quarter at Marshall. On December 20th, a successful 60-second test of all 8 engines was conducted. An earlier test on December 2nd had been terminated by a malfunctioned sensor at 1.7 seconds. Difficulties involving excessive low temperature of an engine component were corrected before the second firing. Plans are now underway for a new Saturn static test firing stand to be located about a mile west of the one presently in use. Addition to this facility will enable the center to conduct 2 booster captive firing operations in the same period. Atron, a division of Aerojet General Corporation, has been selected to do the engineering and design criteria work on the new stand. This phase is expected to require about 7 months. Construction contracts will be awarded separately. Ultimate cost of the static test facility will be $10,800,000. Meanwhile, also in the test area, a striking new landmark rose against the skyline as the new dynamic test facility, shown in this artist's sketch, was erected. The 204-foot-tall structural steel tower looms 27 feet higher than the nearby static test stand. The new facility, begun last July, will be used to determine structural bending frequencies of the entire Saturn vehicle while on launch support arms, and the structural frequencies of the vehicle while suspended to simulate free flight conditions. Other tests, such as propellant loading and the resultant structural deflections, will be conducted. The facility will be finished in the spring of 1961. As the first Saturn booster was being put together in the Fabrication and Assembly Engineering Division, hundreds of engineers and technicians were at work in other Marshall shops and laboratories, building and testing the many complex components which go into the great space vehicle. For instance, this control computer, assembled by the Guidance and Control Division. When aboard the Saturn, the control computer will accept electrical signals from various sources within the vehicle which sense vehicle performance. Then, it will automatically perform suitable computations and send electrical signals to the engine swivel apparatus for proper control of the vehicle flight. The computer is of modular design. The various circuits have been designed as independent modules which can be assembled and tested separately and plugged into the computer. Among other components undergoing intensive testing at the center were the vehicle's telemetry antennas, 6 of which are used on the booster to radiate the power generated by the 8 telemetry transmitters. In this test, the impedance characteristic of a telemetry antenna is being plotted. The impedance measurement being made provides an indication of the antenna performance over the band of frequencies to be transmitted. In another test, an antenna radiation pattern is being recorded. A 1/20th scale model of a Saturn vehicle is rotated while a fixed antenna transmits a radio frequency signal to miniature antennas on the model. The amplitude of the received signal is then recorded as the model rotates, providing a plot of relative signal strength versus viewing angle. In another Marshall laboratory, detailed experimentation involving the actuators for the Saturn booster was being carried out. Hydraulic arms activated by the vehicle's guidance and control system, the actuators will gimbal the 4 outboard engines of the Saturn cluster of 8 during flight to hold the Saturn on course and maintain proper attitude. The actuators are capable of exerting a force of 12,000 pounds from a source pressure of 3,000 psi. Tests check the ability of the mechanical and electrical components to satisfy the design parameters set up as requirements for gimbaling the engines. As shown in this single-engine static test firing to provide guidance and control for the huge vehicle. At the Aeroballistics Division, a program of aerodynamics research and development was being conducted in support of the center's present and future space programs. Examples of this work were the cold jet tests run to aid in the analysis and evaluation of the rocket engine flow of the Saturn booster as it impinges on the launch deflector. Using a 1/25th scale model of the Saturn booster base, an investigation of base flow patterns was made as high-pressure air, 500 psi, was exhausted at Mach 3.18 through nozzles onto the model deflector. The flow of the gaseous exhaust of the Saturn engines is simulated by the air jet. By taking pressure measurements on the base and by using various flow visualization techniques, engineers can determine flow patterns that will exist around the booster's base. In January, a pebble bed heater is to be installed in the air supply so that the engine flow may be heated to 600 degrees Fahrenheit. As work on the first Saturn booster neared completion, dummy upper stages were being built to provide an entire vehicle to test booster propulsion, control, and structure. The dummy second stage, called the S4 stage, was fabricated and assembled at Marshall. The dummy stage uses as its principal part a modified 105-inch diameter tank, similar to that used for the center tank in the booster itself. Steel struts, or longerons, fabricated at Marshall, were joined to the tank and a metal skin attached, thus bringing the dummy up to the live stage's diameter of 220 inches. Assembly work began in late November, using an assembly fixture which had been provided by the Lockheed Aircraft Corporation. The 105-inch tank can be water ballasted to simulate the weight of the actual second stage. Assembly of the dummy is scheduled for completion in late January 1961. Douglas Aircraft Company, contractor for the live S4 stage, is now making a full-scale mock-up of the front and rear sections of the stage at its plant in Santa Monica, California. The mock-up is necessary for study of problems which will be involved in building the actual stage. The live S4, about 41.5 feet long, will utilize four 17,500-pound thrust liquid hydrogen, liquid oxygen engines developed by the Pratt & Whitney division of United Aircraft. The first three Saturn vehicles flown will have dummy second stages. A dummy third stage, called S5, is being made by Convair Astronautics at San Diego, California. Convair will also make the live third stage, a 10-foot diameter modified Centaur stage using two liquid hydrogen, liquid oxygen engines similar to those in the second stage. Convair is preparing a proposal for the S5 contract. Dummy S5 stages will be used in the first 6 Saturn vehicles. As the first Saturn vehicle took shape, construction of the unique river barge, which will transport the booster from Huntsville to Cape Canaveral, was being done at Todd Shipyards in Houston, Texas. The Saturn booster, 82 feet long and 21.5 feet in diameter, is too large for conventional shipment by rail, highway, or air. So, this one-of-a-kind barge was designed for NASA by the Army Transportation Corps. Cost of the craft was $344,800. The barge has been named Palaemon, for the Greek sea god known as a protector of ships. It is 180 feet long and 38 feet wide and has a weight displacement of 450 tons. While the Palaemon was being built in Houston, construction of a slip and dock to accommodate it was completed on the Tennessee River at the Marshall Center. The booster will be transported by road the 5 miles from the assembly area to the dock. Loading and unloading of the booster will be accomplished by use of a wheeled carriage or dolly, which will support the booster through all phases of transit. In late November, the Palaemon arrived at its new home port in Alabama after a 16-day, 1,500-mile trip along the Intercoastal Canal from Houston to New Orleans, up the Mississippi River to Cairo, Illinois, on the Ohio River to Paducah, Kentucky, and then the rest of the way on the Tennessee. Loaded with its booster cargo, it will take a similar trip back to the Gulf of Mexico, then around the southern tip of Florida to reach Cape Canaveral. This route is about 2,200 miles and will take 18 to 25 days. At its destination, work is proceeding on an unloading area where the booster will be taken off the barge and transported to the launch site about 1 mile away. At the launch site itself, known as Complex 34, where the Saturn will be fired in September of 1961, major structural assembly has been finished on the 310-foot-tall Saturn Service Tower, second highest structure in the state of Florida. The Saturn blockhouse, completed last July, was being fitted out with interior equipment such as racks, panels, consoles, and wiring. Work is also underway on the propellant servicing area, and construction of the launch pedestal is continuing on schedule. As Complex 34 progresses, design criteria are being established for construction of a second Saturn space vehicle launching site, to be known as Complex 37. The additional complex will be needed to support anticipated vehicle firing rates and to serve as a backup for the first complex.